Hello everybody, welcome to this week's seminar. It's my honor to introduce Vadim Semenov. Vadim got his PhD from University of Chicago in 2019, just before the pandemic, and then he moved to Harvard as a Hubble Fellow and then an ITC Fellow. So today he will talk about, he's an expert in galaxy simulations, particularly feedback star formation and a lot of also the disk formation. And today he will talk about the regulation of star and galaxy formation. Take it away.
Oh, awesome. Thank you. Yeah, thanks everyone. It's really nice to be here, and thanks so much for the invitation. I really enjoy this place and having so much fun, and looking forward to meet everyone. So yeah, today I'll show you some of my work on the star formation and galaxy formation, what we learned from the simulations. So first of all, straight to It worked? Okay.
No?
It works. Awesome. Yeah, okay, so most of the star formation in the local universe happens in this disk galaxy, just like our own Milky Way. And nowadays we're living through this paradigm shift in our understanding how this disk galaxies actually form. And so recently it was thought that these galaxies form only late in the universe, and this was motivated by observations mainly by Hubble and ground-based telescopes of the higher shift universe, where the galaxies look like this. So they were like really clumpy, irregular, nothing like normal, nice disks that we see around us. And this motivated this picture of disk assembly epoch around the cosmic noon. So it was thought that these galaxies, they form at low redshift below redshift 2 and 1. However, the problem with these observations is that they are sensitive to rest frame UV at this redshift. So essentially it means that they are biased to actively star forming environments. And then with the advent of ALMA, it became possible to probe gas kinematics at these higher redshifts. And it really revealed the existence of this really massive, dynamically cold gaseous disks at very high redshifts, out to redshifts 6 or 7. And nowadays with GWC, we can also probe this redshifts with the rest frame optical. And what it showed over the first year of observations is that these galaxies actually are prevalent out to very high redshifts. And in fact, you can see disks all the way to the highest redshifts where some reasonable quantitative statements can be done about morphology and kinematics of galaxies. So clearly this shows that these galaxies are prevalent not only in the local universe, but they form very early, and they exist throughout the history of the universe. Substantial progress was also made in from the theoretical side in understanding galaxy formation using simulations, and even in early days of galaxy simulations, it was hard to even get something remotely resembling these galaxies, but this changed dramatically. So this was made mainly by the advancements in dynamical solvers, and particularly inclusion of physics like sublimation, feedback, and feedback-driven galactic outflows that appears to be very important for disk formation and survival. So nowadays, state-of-the-art simulations that treat all these processes that can routinely produce reasonably realistic galaxies, like this one shown simulation in Ricardo with Ramses. So essentially, what inside the simulations give us is this picture of different phases of galaxy evolution. So you can see this early stage where galaxy formation is very violent, it's dominated by this active gas inflow from the intergalactic medium with the active mergers. And at some point, disks emerge out of this early chaotic evolution. Then you can see how their properties change over cosmic time. So similarly, nowadays, it's also possible to even see this timeline of disk evolution and different phases of disk assembly in the real data in our own Milky Way. Using this approach, so-called galaxy archaeology, we can dip into the present-day distributions of chemistry and kinematics of stars and learn about Milky Way's past. And this kind of studies, they were facilitated by the advent of large astrometric and kinematic and spectroscopic surveys like Gaia, H3, Apogee, and others. And out of these studies of the recent years, this coherent picture of galaxy assembly emerges, which is nicely summarized in this plot from the paper that Bryce at Harvard is working on with Dan Chandra, where on the y-axis it shows the so-called orbital circularity of stars, of nearby stars in the Milky Way, which essentially shows how disky or spheroidal stellar population is as a function of the metallicity, which in this context can be thought of as a proxy for the formation time and so on. Okay, that's what we can discuss. And the generic picture which is seen from this data is that at high metallicities, the stars that form relatively recently, they assemble in this nice disk that also shows some interesting features, like this kinematically cold thin disk, the highest metallicities, and then older thick disk. But what was discovered only recently, last year, in a series of papers by several different groups, independently, is the existence of this dynamically hot spherical component that resides in the inner part of our galaxy, that's thought to reflect this early phase of galaxy evolution from this chaotic, violent galaxy formation made by accretion and mergers.
So this component is distinct from the spheroid. Kinematic.
So it's it is spheroid, but it's really low metallicity. So it's yeah.
The classical.
Yeah. In addition to this, there is also a stellar halo, which is thought to be which is a remnant of merge. So it's X2 component, which is brought in by mergers. But this one is the stellar population which was born in the progenitor of the Milky Way before the disk was formed. And in fact, now we can from this data we can actually see the formation of the Milky Way disk, and it happens really quickly, so that over the span of metallicity by a factor of 2, the disk emerges out of its chaotic evolution. This was the discovery.
But then it's still true that most of the material that's the stars at disk.
Mostly, yeah. So actually, this
that was a simple admiral ray.
Yes. The mass of this, the mass is quite small, and I'll show it a bit later. And it's important, yeah. So yeah, one of the insights about disk formation was that that this data actually solidified our picture that was suggested before, that the Milky Way disk is quite unusual. So it formed quite early, and this is a comparison of this Milky Way data with the simulations here. It's with the cosmological volume simulation CG50, where so these different lines show Milky Way mass galaxies, and also this spin-up feature in a bit different statistics. It's in the rotational velocity instead of time moment, but the idea is the same. There is this sharp spin-up feature where it was discovered by Belcourt and Kravtsov last year, and we can see that in cosmological simulations, typical Milky Way disk galaxies form their disks on average later than the Milky Way. Only roughly 10% of the galaxies can form disks as early as highlighted with this red line. So this means that Milky Way is on the one hand unusual, but also it's not very uncommon. So it's consistent with our understanding of galaxy formation. But one important insight is that the origin of this scatter in the formation times of the disk. So these galaxies that spin up on different times, they mainly differ by how they assemble their mass. So the galaxies that spin up early simply form most of their mass early on, and then they stay around without significant effect of mergers. While the galaxies that spin up later, they assemble over longer periods of time, and they can experience significant mergers that destroy their disks. And related to this is this question of the mass of the early galaxy, because this assembly of disk related to mass assembly history also suggests the existence of a characteristic mass threshold of the galaxies above which galaxies then form disks. And typically, and the picture like this was found in many different simulations. This is the example from our paper where we show that in the halos below roughly 10 to the 11, galaxies typically not disky, and then really rapidly at more massive galaxies, disks form. So this threshold corresponds to roughly 10 to 11 solar masses in halo mass, or the mass of the stellar component 10 to the 9. And the exact origin of this threshold is not quite clear, and there are different scenarios that discuss. So, for example, maybe when the halo becomes massive enough, it becomes hot, so there is qualitative change in the accretion regime from this accretion fed by cold streams in the cold mode to this coherent smooth accretion in hot mode. But there are also other models like there can be qualitative changes in the gravitational potential in the center. So I'll not go into details that much about this, but I'll be happy to talk about this later. But what's more points now is that these values of the mass threshold for disk formation, they're consistent with this estimate of the total proto-galaxy mass observed in the Milky Way. And also, the mere existence of this threshold makes this abundance of disk galaxies at high redshifts not as surprising, right? So these are just massive galaxies that assemble their mass early on, so they are diskier and they are likely to evolve to more massive galaxies nowadays. So now to
same threshold, kind of for all redshifts.
so these are specifically for the galaxies that end up being Milky Way-like at redshift 0. But in other studies also looked at more uniformly looking at the function of mass and redshift, and typically it's in the same ballpark. Although there's significance cut.
And the fact the Milky Way as a close companion, is that connected?
Sorry?
Is there a connection between high angular momentum early disk formation and a close companion like, low group type environment?
So in simulations we do not see it. So there is not strong correlation between the formation time but some simulations do report. So for example in fire simulations, it's used where when there are like group environments, they tend to form earlier. But these are zoom-in simulations, so it's a question of how samples selected. So it's not clear. Okay, so to understand the subsequent evolution of galaxies, it's really convenient to think about this regulator type of bathtub-like models, which can explain the galaxy evolution to the first order. So the galaxy in this type of models can be thought of as a gas reservoir, which is converted into stars at the characteristic time scale, so ignition time. Then this reservoir is supplied by new material from the accretion of intergalactic gas, and the gas can also be removed from the galaxy by feedback-driven outflows, and these outflows are typically parameterized by this so-called feedback Mass-Volume factors, the scale with the star formation rates, but these Mass-Volume factors can be dependent on purpose of galaxies. So it's a big question in the galaxy formation what exactly this dependence is. But together, if we just take these parameterizations and we can write down this very simple equation for based just on mass conservation, and so we can put in these parameterizations and derive the equation that will govern the gas content in the galaxy, which we then can connect with star formation rates, integrate all these equations and get the evolution of galaxy for cosmic time. So what this equation tells us is that the characteristic time of evolution of galaxies depends on this gas depletion time and on the mass loading factor of outflow. So in the end, in order to understand galaxy evolution, we need to understand three things. So we need to understand how the physics of gas accretion, how gas is supplied to the galaxy. We need to understand how feedback drive gas out of the galaxy. And we also need to understand this depletion times. All the information about the star formation is encapsulated in this quantity. And as I'll show in the talk, this quantity reflects the internal dynamics of galaxies and the coupling of this dynamics with the processes of star formation feedback that happens on small scales, or scales of individual star forming regions. And this will be mostly the topic of the rest of my talks. Essentially, I'll be focusing on these two questions. One is what is the origin of gas depletion times, how we can understand it, and then based on these insights, I'll argue that the way how star formation simulations is modeled should be improved. and I'll, if I have time, I'll show some ideas about how this can be done. Okay, are there any questions at this point? Okay, so here just some nice images, but what I wanted to show here is that the star formation in galaxies is a very complex process. Right? So if we look at the ISM of galaxies, we see this structures on the range of scales. So it's on global scales, it's the spiral arms and this huge bubbles, especially with this recent GW2 pictures. If we zoom in down to the scales where stars form, so here, for example, is the typical scale of absolute star forming regions, we still continue seeing these structures all the way down to smaller scales. So, and this is a generic view of star formation and generic problem for why it's so complicated to model. So the stars, they form from the collapse of self-rotating cores on the sub-parsec scales, which is a part of this turbulent cascade that extends out to the galactic global disk scales, and then star formation feedback couples these all scales together by driving this, creating these bubbles, driving turbulence in the interstellar medium, and even removing gas from the galaxy. So in these details, star formation is an insanely complex, multi-scale, multi-physics process. But at the same time, when we zoom out and look at galaxy and star formation on larger scales, on galaxies larger scales, then very tight, nice relations emerge, like this Kempka-Schmidt relation, which is a relation between the star formation rate, surface density, and the amount of gas, or gas surface density. So galaxies, there are different types, occupy relatively narrow ranges in this space. And the depletion time, it reflects the normalization of these relations. So it tells us that these relations, they tell us that the typical time scales on which gas is converted to stars is of order of billions of years. For example, for the Milky Way, this time scale is of order of 5 to 10 billion years. And if we only include molecular gas, then relations like this, they typically become tighter, but the depletion time value stays of the same order, so roughly a few billions of years. And this value of depletion time, of billions of years long depletion time, is actually quite, just be quite a puzzle, because it suggests it's much longer than any time scales relevant for star formation in interstellar medium. So it means that star formation globally in galaxies is very inefficient. So, for example, the typical dynamical time scales in the interstellar medium, such as turbulent crossing time or local freefall times, they are of order of tens of millions of years. So the orbital period of the galaxy is order 100 of millions of years, which is significantly shorter than global depletion times, which means that this gas is converted into stars over many dynamical times. At the same time, this global inefficiency cannot be explained by the local inefficiency alone. So if we look at the individual star forming regions, they are also very inefficient. So usually their efficiency is parameterized with this so-called star formation efficiency per freefall time, which is observed to be of order a few percent, meaning that on their freefall times, star forming regions convert only a few percent of gas into stars. But the typical depletion time of star forming regions are of order of hundreds of millions of years, which is still significantly shorter than the galactic average. So here, this is the inverse of depletion time. So in order to understand the depletion time, so we need to explain both why the depletion time is significantly longer than the dynamical timescales, and why it's also longer than the depletion time of actively star-forming regions. And this was the focus of a series of works that we published a few years ago, where we looked at this with simulations, and simulations appear to be very useful for that. So this is an example of the simulations, idealized Milky Way size galaxy simulation, and here this movie shows just different quantities from the simulation: gas density, temperature, and this is something special about this simulation. It's turbulence velocity on unresolved scales, which I hope I'll have time to talk more at the end. But the main takeaway that I want to take from this movie is that when we look at the evolution of galaxy on the long time scales, here's several orbital periods, which becomes comparable to the global depletion times. On this time scale, all these quantities, they change rapidly, right? So the entire ISM on this star formation time scales boils like water in a kettle, and the long depletion times in active star formation actually somehow emerges from this rapid evolution, which is consistent with the short dynamical time scales. But to understand how this happens, it's quite insightful to look at the distribution of gas in planes like this, where, so in x-axis it's the gas density, and on y-axis it's total velocity dispersion, should be thought of as the total support of the gas. So essentially, it's useful because the location of gas in this plane, it determines whether gas is actually star-forming or not, so we can separate the ISM into star-forming and non-star-forming phases based on the location of gas here. And this is because this is motivated by the theoretical models of star formation in the turbulent gas that typically predicted the total efficiencies of this star forming regions. They depend exponentially on the so-called real parameter, which describes how important turbulent support is compared to gravity. So these lines here show the fixed values of this real parameter, and when gas goes in this corner of the distribution, it becomes the turbulent support becomes less important compared to gravity, and gas becomes more and more bound. But because the dependence of the efficiency is exponential, and the values of real parameter in the interstellar medium span orders of magnitude, we include also the warm part of the medium, and this exponential dependence can be thought of as a sharp threshold. So essentially, we can separate the entire ISM into axially star-forming state that forms stars and the non-star-forming state. And then in simulation, you can see how gas evolves between these two phases. And so we can follow evolution of individual gas parcels, and this is what we see. So we can think about this as the typical trajectories of hydrogen atoms in the interstellar medium. And what happens is when gas evolves from the non-star-forming state into star-forming state, it spends only a small fraction of time in the star-forming state before the process like efficient feedback and dynamical process can destroy the star-forming regions and move gas back into non-star-forming state. So as a result, although each such cycle is short, gas has to go through a large number of cycles going back and forth between star-forming and non-star-forming stages, because on each cycle it converts only a small fraction of mass into stars. And this is what makes the depletion time long, even though the duration of individual cycles is short. So this picture is very intuitive, and actually it's very similar to what happens in any sport competition. So for example, in soccer there's exactly the same situation, because so the typical time scale that takes a player across the field is order of 10 seconds. But at the same time, with 90 minutes match, the goals are scored only a few times. Right? So it means that the efficiency of scoring in soccer is very low per dynamical time. And the origin of this inefficiency is exactly the same. It's because when players of the offensive one team approach the penalty area, they don't just go ahead and score, they face feedback from the defense. Right? And as a result, they have to cycle through the whole field many times before they accumulate enough probability close to the penalty area so that they can eventually score. And in the end, this is the same what happens in the interstellar medium, except that there is a competition between the processes that create and destroy star-forming regions. So now, having this simple picture in mind, we can actually write down a very simple analytic expression for depletion time. So for this, we can write, just by definition, we can slightly rewrite the depletion time of gas as the depletion time in this actively star-forming state, divided by the mass fraction of gas in this state. So this depletion time of star-forming gas will depend on properties of individual regions. So for example, their viral parameter, their local star formation efficiencies, their densities. And the fraction of star-forming gas will be the response of the ISM to this local process. So essentially, if we can rewrite this fraction as the ratio of the residence times in star-forming and non-star-forming states. And so the residence in the star-forming state will be the time scale on which process dispersed star-forming regions, and residence time in the non-star-forming state will be the time scale on which these regions can be recreated from the average ISM on the dynamical time scales. And then we can put together this expressions and write this very simple expression for depletion time that consists of two terms. So first, it's depletion time of total gas is the depletion time in star-forming state. So this is how much gas has to spend in the star-forming state before it's depleted, plus the total time that gas spends outside the star-forming state. And it consists of a duration of one cycle times the total number of cycles. And the total number of cycles is, again, the depletion time in star-forming state divided by the lifetime of the regions. And this number of cycles can be very large because of two factors. So first of all, the star formation is locally very inefficient, so the depletion time of star-forming gas is long. But at the same time, they are short-lived, so they're quickly dispersed by stellar feedback. And in realistic, in real star-forming regions, this, from what we know about real star-forming regions, the number of cycles can be of the order of a few dozens, hundreds. So essentially, each atom in the ISM has to go through dozens and dozens of regions before it ends up in a star.
So what processes determine these time scales, right? I mean, so cooling, I guess, must be important. Similarly,
yeah. So
velocities.
Yeah, essentially. So this you mean this the formation time? Okay, yeah. So what useful here is that these different time scales, they actually encapsulate different physics, right? So this lifetime and non-star-forming state, it's like how from the average ISM how gas goes into the how it becomes dense and eventually becomes star-forming. So it can be time scale between spiral arms, plus given parcel of gas, right, or in how turbulent medium, how often it's compressed or decompressed. Yeah, so it's typically, but typically it's dynamical time scales. So this will be set by the crossing times in turbulence on this scale height, or like the time scales of the spiral arm passage. Cooling time are usually not that important here because cooling is essentially the cooling time becomes short when gas becomes dense enough. So essentially it's either long in the average ISM, but then when the gas is compressed, say by spiral arms, gas just cools down, right? So the cooling time becomes irrelevant. It's always short enough. It's always short enough in the ISM.
There's no processes that are damping the turbulence velocities at small scales.
So this is like more about the scale, more like between galactic scales and the scales of star-forming regions. So how we create star-forming regions from the average ISM. But in fact, so here the only assumption here is the mass conservation, right? So in principle, this can be also used on smaller scales, which is a really nice segue to the next slide. So here, I just want to advertise the work that student Sabrina Apple at Rutgers is doing, where she was looking at the origin of local star formation efficiency in the simulations of turbulent gas. So these are much smaller scales, and there you can also explore similar ideas, right? So she was looking at the rates of gas evolution, how gas expands and compresses, and there's a very similar picture where the total star formation rate is determined by the competition between these fluxes that themselves depend on different pieces of physics that are put in simulation, like driving of turbulence or magnetic fields or solar feedback. So, and in the end, this all translates into the strong dependence of the local star formation efficiency on this process. There was another question?
Yeah. How did you calculate the turbulent velocities? Did you assume that molecular gas is actually a gravitational collapse? Because in the molecular clouds, there are velocity gradients within the clouds.
So yeah, I hope I have time, but so this essentially there's a dynamical model that captures onset of cascade on result scales and evolves unresolved turbulence on the fly. So essentially it's some great prescription for turbulence. Yeah, I hope I'll have time to show more about. Yeah, so now if we go back to this large scales, we can understand, using this framework, we can understand connection between the global and the local star formation. So again, in this nice cartoon, if we look at in the simulations at the same scales where stars form, we never see nice structures like this. Instead, we have to deal with something like this, right? So, so this, for example, this turbulence is not resolved. We need to track it in subgrid fashion, and we also need to track model star formation and feedback as subgrid process as well. And the common choice for modeling star formation is to parameterize it through this local star formation efficiency, which is motivated by the way how it's done in observations. But in simulations, this efficiency is often treated as a tunable parameter. So some gas is designated as star forming by using dense temperature or other thresholds, and then this efficiency parameter is a number which is constant in space and time. And this model can be used to understand the dependence of global star formation rate on this local star formation efficiency. So these points here are simulations with that assume different values of this local efficiency, and the y-axis is this global star formation rate or global depletion time. So there is quite non-trivial dependence of the global star formation rate on efficiency. There are these two regimes. In one regime, star formation rate strongly linearly depends on efficiency, and the other it does not. And this line is the prediction from this model, so it can be used to explain these different regimes. So this is because different terms in this expression depend differently on star formation efficiency. So when so depletion time of star forming gas explicitly by definition depends scales inversely with efficiency. And then at the same time, in the regime where the lifetimes of star forming regions is controlled by feedback, the lifetime of star forming regions also scales inversely with efficiency. So when efficiency is increasing, the same number of stars forms the same mass of stars form proportionally faster, so they inject proportionally more momentum and energy and disperse the region sooner. So as a result, this linear correlation with efficiency cancels out in the second term, and then only the first term depends on efficiency. And when the star formation efficiency is low, this depletion time of star forming gas will be dominant, and the global depletion time will simply follow this relation. So this is a regime of inefficient feedback. But at very high efficiency, the second term will become dominant, which is insensitive to efficiency. And in this regime, the global depletion time saturates, and it doesn't depend on star formation efficiency. And this is the result that was found in many different simulations. Like, for example, this is a plot from FIRE, where they changed the local star formation efficiency by 4 orders of magnitude, but the global star formation rate is essentially the same. And it's, this model naturally explains this regime, this independence of the global star formation rate of the efficiency. However, it's important to note that it doesn't mean that the star formation efficiency doesn't matter. It just shows that the global star formation rate or depletion time is insensitive to efficiency, so it cannot be used to constrain its value, while other processes in galaxies will depend on the choice of efficiency. So, for example, the amount fractional star forming gas in this regime will linear scale with efficiency. So by increasing efficiency, the star formation rate stays constant at the expense of decreasing the amount of dense gas in the galaxy. So we need some other statistics to constrain the efficiency in this regime. And
So there is some time lags between these two terms, right?
so again?
There are some time lags between, because like when you have a high local star forming efficiency, it will have stronger feedback, but it's kind of lagging behind the star forming phase a little bit, right?
So in this regime, what happens is, so this time scale, it reflects the gas evolution outside of star forming regions, right? So essentially, diffusion time will dominate by the time that you need to form star forming regions, right? So the star forming region will be dispersed instantly as soon as it forms because the efficiency is so high. But to deplete the gas, you still need to go through all the cycles.
I was just thinking about does it depend on what the star forming indicators you use to measure this stuff?
Yeah. So one consequence actually, yeah. So for example, the star formation will be more bursty, right? So this is like averaging over some time scale. So because here, if we increase efficiency, then the same amount of star formation will be concentrated in less and less star forming regions. So there will be, simply from Poisson noise, there will be significant variation, right? So then, in principle, this can be probed by looking at different indicators.
Sorry, I missed the definition of TSF. What's TSF?
Yeah, so T, it's a resonance time of star forming, so it's lifetime of star forming regions. It's how quickly star forming regions can be dispersed.
Dispersed by tidal force.
Yeah, in this case, so it depends. So in this case, when efficiency, local star formation efficiency is high, it's mainly dominated by stellar feedback. So it's how quickly young stars can disperse the star forming region. But in other regimes, it can be other effects. And for example, here, in this regime, we find that it's mainly a dynamical process, like for example, tidal or like shearing turbulence in the interstellar turbulence. So yeah, the exact process behind this time scales can differ depending on the region. Yeah, so one way how this local star formation efficiency can be constrained is by looking at the scales of the ISM structure on small scales, on sub-kiloparsec scale. So as we, so this tight correlations, like Inca-Schmidt relation, they appear on kiloparsec and larger scales. But when we look at tracers of dense gas like CO and star formation like H alpha on sub-kiloparsec scales, they start to decorrelate, meaning that this nice correlations break down. And this small scale decorrelation is largely evolutionary. So essentially, when we look at CO, we see instantaneously the distribution of molecular gas, while H alpha reflects past star formation, which already dispersed some of these molecular regions in which stars were formed. So mere existence of this decorrelation tells us that the time scale in which these star forming regions disperse must be short. It must be short, comparable to the time scale on which stellar population produces ionizing radiations, roughly 5 billion of years. And statistical details about this decorrelation will imprint some information about how exactly this dispersal happens. So we also explored it in this idealized simulation similar to the one which I showed before, except that this one was designed to match this NRC 300 galaxy, which is the intermediate dwarf galaxy where this decorrelation was measured. So it was designed to match it in terms of the global structure, like mass, radial profiles, different bounces, velocities. And also we're a bit more careful about what feedback process includes. So for example, the simulation includes on-the-fly radiative transfer with a couple of the molecular chemistry. So this is one of the processes that can create this decorrelation. So here in this panel, this is the distribution of radiation field, and we can see these bright spots that appear where star clusters form. So they produce this intense radiation that can dissociate this dense molecular regions in dark color. And again, so we also model this end result turbulence and couple modeling of star formation efficiency with it. So we, instead of assuming that the value of star formation efficiency, we forward model it, and by using this theoretical models of star formation turbulent gas and plugging them in as a subgrid model, because we can predict what's the real parameter of gas in each resolution element. And this is the map of the star formation efficiency in this galaxy, so it changes dynamically both in space and time.
Just quickly, in that expression for the real parameter,
Yeah.
what do you choose for the L? Is that your resolution scale?
So yeah, this is the resolution scale.
So you're evaluating real parameter specifically on the resolution scale.
Yes, so this is motivated also motivated by subgrid turbulence model because so we model the velocity expression at the resolution scale as well. So
You're assuming a normal L1/2 cascade.
It's implicit. It's not. It's implicitly enters for the way how the model is calibrated because it's calibrated in direct simulation turbulence. So essentially, it's assuming that the props of turbulence in the galaxy are similar to the environment where the model is calibrated. So yeah, now we can take this galaxy, zoom in into the it's ISM, see where the young stars and molecular gas are that will be observable in H-alpha and CO. And already from here, from this, we can see that there's a quite significant level of decorrelation. One way to quantify it is by placing apertures on the peaks of, let's say, molecular gas and measuring depletion time. So if the aperture size is small enough, it will be biased towards long depletion time because it predominantly includes molecular gas. But then if we increase the aperture size, we'll include more and more traces of both types, so the depletion time will converge to the galactic average value. If we repeat the same exercise for peaks, for apertures placed on H-alpha or young stars, then we'll get this similar relations but flipped. So together, this will produce this tuning fork-like diagram, which was introduced by Shuba and others 20 years ago for N33, and now it's also widely used in observations to quantify the star formation feedback cycle. So essentially, the shape of the tuning fork and its opening tells us how decorrelated star formation and gas tracers as a function of scale. So the strong decorrelation will result in wider opening of the tuning fork. And this model, where we include all these different pieces, it can reproduce the observed decorrelation in NGC 300 remarkably well, especially on the scales above 80 parsec or so, which by itself is quite non-trivial because it was shown that getting the statistics right in simulation is really tricky. So usually there is significantly stronger correlation between dense gas and star formation, recent star formation simulations. And the reason for this, why it's hard, is because the statistics depends on multiple different things, and the modeling of star formation is one of them. So here, this is again the diffusion simulation here is shown with black. It's the one where we forward model efficiency. But also, if we use a common prescription where efficiency is fixed and change its value, then the opening of the tuning fork will be sensitive to the choice of this efficiency. So by choosing larger efficiency, the decorrelation becomes stronger. And this galaxy is in this regime where the global star formation rate is insensitive to this choice. So in all the simulations, the global star formation rate remains roughly the same and it's consistent with what is seen in NGC 300. So we are in this regime where depletion time is set by the second term, so the dependence on efficiency cancels out in these two terms. So the reason why the tuning fork is sensitive to the choice of efficiency because it's individually sensitive to the lifetime of star forming regions, this TSF, and we can also see this directly in simulation because we can look at the distribution of the time scales that gas spends in star forming regions is shown here. So when we choose low efficiency of star formation, there's a long tail of this long-lived star forming regions that create stronger correlation with between molecular gas and young stars. If we increase efficiency, this long-lived regions are dispersed faster, so we get rid of this tail, and the correlation becomes weaker.
So this will also depend on the strength of your feedback. Right?
Exactly, yeah. So one temptation. Exactly. The one temptation is that okay, maybe something like this can be used to calibrate efficiency, right? but exactly the problem is that it also depends on what we do about star feedback, right? So if we calibrate efficiency based on the statistics, then say weaker early feedback can be compensated by selecting higher star formation efficiency, which nicely brings me to the last part of my talk. So how much?
We have 10 minutes.
I mean, it's okay. I'll do my best. Yeah. So yeah, I'll try this to be. It might be a bit technical, but I'll try to explain it in simple terms. So because I really like the whole idea. So now how we can go forward, right? So for this we need to there's some prescription for this unresolved scales. We need to model this subgrid and turbulence, and modeling star formation is only one of the things that can be improved if we have some information about this unresolved scale. So pretty much any other process that depends on unresolved structure of gas can also be modeled based on turbulence, like chemistry or cooling rates in the scampy medium or transport of cosmic rays, modeling of lines, microscopic dynamo, so anything that depends on turbulence. So it's very useful in the context of galaxy simulations. So you can think of the turbulence as this kinetic energy injected on some large scales, and then it cascades down to smaller scales, where eventually dissipation becomes important and it's converted into heat. But this physical dissipation scales in galaxy simulations can never be resolved. They are many orders of magnitude below the resolution. So what happens instead is that this energy is dissipated at the resolution scale. And if we think about this in terms of energy reservoirs, then this energy from kinetic energy from resolved motions goes straight to the thermal energy at the resolution scale, and the dissipation done purely by numerical effects, numerical viscosity. So the idea of this subgrid turbulence is to reintroduce this additional energy reservoir, which will represent this missing part of the cascade. And then we also need to include, so we include the extra equation that describes how this energy evolves, and we also need to model extra terms which will describe the coupling between resolved and subgrid scales. And this broadly, this type of models is called large eddy simulations, and it's widely used in simulation of terrestrial flows and many different applications, from aerospace engineering all the way to geophysics and climate models. And this is also the type of simulations that I've been using in this galaxy simulation that I showed before. And so the whole complexity of this model and the art comes into how to model these extra subgrid terms that couple resolved and unresolved scales. At the same time, know that if we do not necessarily need the explicit model to model turbulent flows, as long as the resolution is high enough so that we can resolve it as part of the cascade. So this is, for example, a compilation results from code comparison paper where the turbulent box was simulated with a bunch of different codes, and on the large scales where the turbulent cascade can resolve, they all correctly model the cascade of kinetic energy, and the difference appears only on small scales where they differ in, well, different codes differ in hydrodynamical methods that they use, so the numerical dissipation is different, and the difference appear and is clear at the resolution scale. So, and this is actually a generic property of turbulent flows, that the dissipation rate in simulations, in turbulent flows, it doesn't depend on viscosity. So viscosity only changes the scale on which the dissipation happens. So if we decrease viscosity, then the energy cascade will continue down to smaller scales, but the energy dissipation rate will be set by how much energy is cascading from the large scales, right? So by extension, it means that the rate of numerical dissipation locally, it equals to the energy cascade rate from the resolved scales. And this is the idea that lies behind this concept of implicit large eddy simulations, that this numerical dissipation can be thought of as an effective model built into the hydrodynamical code. But the problem is that for us, it makes for our applications, it doesn't make any good because we need an explicit turbulence field that we need to couple with things like star formation and other processes in one model. So the idea is that in principle, these two different methods can be combined. So we can still model turbulent energy reservoir, but instead of using explicit terms that describe the connection between resolve and subgrid scales, we can simply capture numerical dissipation locally and use it as an implicit source term for subgrid turbulence. So this is the idea, and I have been recently working on testing this very simple model. So essentially, it's really easy to implement because most of the model is already built into any hydrodynamical code that you use. How it can be tested? So, for example, it can be tested against direct simulation of turbulence. So here, this is the simulation of turbulent box, which we can model at high resolution, then coarse grain it to some larger scale, at some scale, and then we can rerun it with the matching scale and use a subgrid turbulence model to try to predict what the turbulent velocity, turbulent energy on small scales should be. And this is a result of the model. So the low resolution solution is much more diffusive because it's more viscous on the scales, but at the same time, the model correctly captures all the correlations between the local turbulent velocity and density, which is really important for modeling things like real parameter because it will combine both quantities. So I'll not, I have more quantitative comparisons, which I'm happy to show everyone, but one thing that I want to show is the more realistic application, this galaxy simulation, where this very simple model actually performs quite similar to this explicit turbulence model. So here, this is the same galaxy simulated with the simple model or with this explicit model that I showed before. And in terms of things like the average subgrid turbulent velocity as a function of Galois-Parsons scale properties like gas surface density or the area star formation efficiency, these models work very similar, which is very encouraging given how simple this model is. So yeah, I'll be happy to talk more about this. And in this, I will just leave my main conclusions. So the disk formation is correlated with the mass assembly of galaxies, and overall the evolution of galaxies can be thought of as interplay between mass inflow, outflows, and the star formation. So to understand this connection between this process, we need to understand the depletion times in galaxies, and I showed this framework that can be used for this that connects global depletion times with the depletion times on regions of actually star forming regions and the process that destroy regions and dynamical process that create the star forming regions. And this model can be used to explain different industry regimes, such as the self-regulation in the limit where stellar feedback is efficient, and the efficiency and global depletion time becomes independent of efficiency. And in this regime, we need this more detailed statistics to distinguish between different efficiency models. And all this points to the fact that model ISM to these details, we need the really predictive models for modeling star formation efficiency, and I showed you some examples how it can be done. Questions? Thank you.